Section 2.3, Analyzing Findings. Learning Objectives. By the end of this section, you will be able to explain what a correlation coefficient tells us about the relationship between variables. Recognize that correlation does not indicate a cause and effect relationship between variables. Discuss our tendency to look for relationships between variables that don't really exist. Explain random sampling and assignment of participants into experimental and control groups. Discuss how experimenter or participant bias could affect the results of an experiment. Identify independent and dependent variables. Did you know that as sales in ice cream increase, so does the overall crime rate? Is it possible that indulging in your favorite flavor of ice cream could send you on a crime spree? Or, after committing crime, do you think you might decide to treat yourself to a cone? There's no question that a relationship exists between ice cream and crime, but it would be pretty foolish to decide that one thing actually caused the other to occur. It is much more likely that both ice cream sales and crime rates are related to the temperature outside. When the temperature is warm, there are lots of people out of their houses, interacting with each other, getting annoyed with each other, and sometimes committing crimes. Also, when it's warm outside, we're more likely to seek a cool treat like ice cream. How do we determine if there is indeed a relationship between two things? And when there is a relationship, how can we discern whether it's attributable to coincidence or causation? Correlational research. Correlation means that there's a relationship between two or more variables, such as ice cream consumption and crime. But this relationship does not necessarily imply cause and effect. When two variables are correlated, it simply means that as one variable changes, so does the other. We can measure correlation by calculating a statistic known as the correlation coefficient. A correlation coefficient is a number from -1 to +1 that indicates the strength and direction of the relationship between variables. The correlation coefficient is usually represented by the letter R. The number portion of the correlation coefficient indicates the strength of the relationship. The closer the number is to 1, whether that be negative or positive, the more strongly related the variables are, and the more predictable changes in one variable will be as the other variable changes. The closer the number is to 0, the weaker the relationship, and the less predictable the relationships between the variables becomes. For instance, a correlation coefficient of 0.9 indicates a far stronger relationship than a correlation coefficient of 0.3. If the variables are not related to one another at all, the correlation coefficient is 0. The example above about ice cream and crime is an example of two variables that we might expect to have no relationship to each other. The sign, positive or negative, of the correlation coefficient indicates the direction of the relationship. A positive correlation means that the variables move in the same direction. Put another way, it means that as one variable increases, so does the other. And conversely, when one variable decreases, so does the other. A negative correlation means that the variables move in opposite directions. If two variables are negatively correlated, a decrease in one variable is associated with an increase in the other, and vice versa. The example of ice cream and crime rates is a positive correlation because both variables increase when temperatures are warmer. Other examples of positive correlations are the relationship between an individual's height and weight, or the relationship between a person's age and number of wrinkles. One might expect a negative correlation to exist between someone's tiredness during the day and the number of hours they slept the previous night. The amount of sleep decreases as the feelings of tiredness increase. In a real-world example of negative correlation, student researchers at the University of Minnesota found a weak negative correlation, R equals -0.29, between the average number of days per week that students got fewer than 5 hours of sleep and their GPA. Keep in mind that a negative correlation is not the same as no correlation. For example, we would probably find no correlation between hours of sleep and shoe size. As mentioned earlier, correlations have predictive value. Imagine that you're on the admissions committee of a major university. You're faced with a huge number of applicants, but you're able to accommodate only a small percentage of the applicant pool. How might you decide who should be admitted? You might try to correlate your current student's college GPA with their scores on standardized tests like the SAT or ACT. By observing which correlations were strongest for your current students, you could use this information to predict relative success of those students who have applied for admission into the university. Correlation does not indicate causation. Correlational research is useful because it allows us to discover the strength and direction of relationships that exist between two variables. However, correlation is limited because establishing the existence of a relationship tells us little about cause and effect. While variables are sometimes correlated because one does cause the other, it could also be that some other factor, a confounding variable, is actually causing the systematic movement in our variables of interest. In the ice cream/crime rate example mentioned above, temperature is a confounding variable that could account for the relationship between the two variables. Even when we cannot point to clear confounding variables, we should not assume that a correlation between two variables implies that one variable causes changes in another. This can be frustrating when a cause and effect relationship seems clear and intuitive. Think back to our discussion of the research done by the American Cancer Society and how their research projects were some of the first demonstrations of the link between smoking and cancer. It seems reasonable to assume that smoking causes cancer, but if we were limited to correlational research, we would be overstepping our bounds by making this assumption. Unfortunately, people mistakenly make claims of causation as a function of correlations all the time. Such claims are especially common in advertisements and news stories. For example, recent research found that people who eat cereal on a regular basis achieve healthier weights than those who rarely eat cereal. Guess how the cereal companies report this finding? Does eating cereal really cause an individual to maintain a healthy weight? Or are there other possible explanations, such as someone at a healthy weight is more likely to regularly eat a healthy breakfast than someone who is obese or someone who avoids meals in an attempt to diet? While correlational research is invaluable in identifying relationships among variables, a major limitation is the inability to establish causality. Psychologists want to make statements about cause and effect, but the only way to do that is to conduct an experiment to answer a research question. The next section describes how scientific experiments incorporate methods that eliminate or control for alternative explanations, which allow researchers to explore how changes in one variable cause changes in another variable. Illusory correlations. The temptation to make erroneous cause and effect statements based on correlational research is not the only way we tend to misinterpret data. We also tend to make the mistake of illusory correlations, especially with unsystematic observations. Illusory correlations, or false correlations, occur when people believe that the relationships exist between two things when no such relationship exists. One well-known illusory correlation is the supposed effect that the moon's phases have on human behavior. Many people passionately assert that the human behavior is affected by the phase of the moon, and specifically that people act strangely when the moon is full. There's no denying that the moon exerts a powerful influence on our planet. The ebb and flow of the ocean's tides are tightly tied to the gravitational forces of the moon. Many people believe, therefore, that it's logical that we're affected by the moon as well. After all, our bodies are largely made up of water. A meta-analysis of nearly 40 studies consistently demonstrated, however, that the relationship between the moon and our behavior does not exist. While we may pay more attention to odd behavior during the full phase of the moon, the rates of odd behavior remain constant throughout the lunar cycle. Why are we so apt to believe in illusory correlations like this? Often we read or hear about them and simply accept the information as valid. Or we have a hunch about how something works and then look for evidence to support that hunch, ignoring evidence that would tell us our hunch is false. This is known as confirmation bias. Other times, we find illusory correlations based on the information that comes most easily to mind, even if that information is severely limited. And while we may feel confident that we can use these relationships to better understand and predict the world around us, illusory correlations can have significant drawbacks. For example, research suggests that illusory correlations, in which certain behaviors are inaccurately attributed to certain groups, are often involved in the formation of prejudicial attitudes that can ultimately lead to discriminatory behavior. Causality: conducting experiments and using the data. As you've learned, the only way to establish that there's a cause and effect relationship between two variables is to conduct a scientific experiment. Experiment has a different meaning in the scientific context than in everyday life. In everyday conversation, we often use it to describe trying something for the first time, such as experimenting with a new hairstyle or a new food. However, in the scientific context, an experiment has precise requirements for design and implementation. The experimental hypothesis. In order to conduct an experiment, a researcher must have a specific hypothesis to be tested. As you've learned, hypotheses can be formulated either through direct observation of the real world or after careful review of previous research. For example, if you think that children should not be allowed to watch violent programming on television because doing so would cause them to behave more violently, then you've basically formulated a hypothesis, namely, that watching violent TV programs causes children to behave more violently. How might you have arrived at this particular hypothesis? You may have younger relatives who watch cartoons featuring characters using martial arts to save the world from evildoers, with an impressive array of punching, kicking, and defensive postures. You notice that after watching these programs for a while, your young relatives mimic the fighting behavior of the characters portrayed in the cartoon. These sorts of personal observations are what often lead us to formulate a specific hypothesis. But we can't use limited personal observations and anecdotal evidence to rigorously test our hypothesis. Instead, to find out if real world data supports our hypothesis, we have to conduct an experiment. Designing an experiment. The most basic experimental design involves two groups: the experimental group and the control group. The two groups are designed to be the same, except for one difference: experimental manipulation. The experimental group gets the experimental manipulation, that is, the treatment or variable being tested, in this case, violent TV images, and the control group does not. Since experimental manipulation is the only difference between the experimental and control groups, we can be sure that any differences between the two are due to experimental manipulation rather than chance. In our example of how violent TV programming might affect violent behavior in children, we have the experimental group view violent TV programming for a specific time and then measure their violent behavior. We measure the violent behavior in our control group after they watch nonviolent TV programming for the same amount of time. It's important for the control group to be treated similarly to the experimental group, with the exception that the control group does not receive the experimental manipulation. Therefore, we have the control group watch nonviolent TV programming for the same amount of time as the experimental group. We also need to precisely define, or operationalize, what is considered violent and nonviolent. An operational definition is a description of how we will measure our variables, and it's important in allowing others to understand exactly how and what a researcher measures in a particular experiment. In operationalizing violent behavior, we might choose to count only physical acts like kicking or punching as instances of this behavior. Or we also may choose to include angry verbal exchanges. Whatever we determine, it's important that we operationalize violent behavior in such a way that anyone who hears about our study for the first time knows exactly what we mean by violence. This aids people's ability to interpret our data, as well as their capacity to repeat our experiment should they choose to do so. Once we've operationalized what is considered violent TV programming and what's considered violent behavior from our experiment participants, we need to establish how we will run our experiment. In this case, we might have participants watch a 30-minute television program which is either violent or nonviolent, depending on their group membership, before sending them out to a playground for an hour where their behavior is observed and the number and type of violent acts is recorded. Ideally, the people who observe and record the children's behavior are unaware of who was assigned to the experimental or control group in order to control for experimenter bias. Experimenter bias refers to the possibility that a researcher's expectations might skew the results of the study. Remember, conducting an experiment requires a lot of planning, and the people involved in the research project have a vested interest in supporting their hypotheses. If the observers knew which child was in which group, it might influence how much attention they paid to each child's behavior, as well as how they interpreted that behavior. By being blind to which child is in which group, we protect against those biases. This situation is called a single blind study, meaning that one of the group's participants are unaware as to which group they are in, the experiment or control group, while the researcher who developed the experiment knows which participants are in each group. In a double-blind study, both the researchers and the participants are blind to group assignments. Why would a researcher want to run a study where no one knows who is in which group? Because by doing so, we can control for both experimenter and participant expectations. If you're familiar with the phrase placebo effect, you already have some idea as to why this is an important consideration. The placebo effect occurs when people's expectations or beliefs influence or determine their experience in a given situation. In other words, simply expecting something to happen can actually make it happen. The placebo effect is commonly described in terms of testing the effectiveness of a new medication. Imagine that you work in a pharmaceutical company and you think you have a new drug that is effective in treating depression. To demonstrate that your medication is effective, you run an experiment with two groups. The experimental group receives the medication, and the control group does not. But you don't want participants to know whether they received the drug or not. Why is that? Imagine that you're a participant in the study, and you've just taken a pill that you think will improve your mood. Because you expect the pill to have an effect, you might feel better simply because you took the pill and not because of any drug actually contained in the pill. This is the placebo effect. To make sure that any effects on mood are due to the drug and not due to expectations, the control group receives a placebo, in this case a sugar pill. Now everyone gets a pill, and once again neither the researcher nor the experimental participants know who got the drug and who got the sugar pill. Any differences in mood between the experimental and control groups can now be attributed to the drug itself rather than to experimenter bias or participant expectations. Independent and dependent variables. In a research experiment, we strive to study whether changes in one thing cause changes in another. To achieve this, we must pay attention to two important variables, or things that can be changed, in any experimental study: the independent variable and the dependent variable. An independent variable is manipulated or controlled by the experimenter. In a well-designed experimental study, the independent variable is the only important difference between the experimental and control groups. In our example of how violent television programs affect children's displays of violent behavior, the independent variable is the type of program, violent or nonviolent, viewed by the participants in the study. A dependent variable is what the researcher measures to see how much effect the independent variable had. In our example, the dependent variable is the number of violent acts displayed by the experimental participants. We expect that the dependent variable will change as a function of the independent variable. In other words, the dependent variable depends on the independent variable. A good way to think about the relationship between the independent and dependent variables is with this question: what effect does the independent variable have on the dependent variable? Returning to our example, what effect does watching a half hour of violent television programming or nonviolent television programming have on the number of incidents of physical aggression displayed on the playground? Selecting and assigning experimental participants. Now that our study is designed, we need to obtain a sample of individuals to include in our experiment. Our study involves human participants, so we need to determine who to include. Participants are the subjects of psychological research, and as the name implies, individuals who are involved in psychological research actively participate in the process. Often, psychological research projects rely on college students to serve as participants. In fact, the vast majority of research in psychology subfields has historically involved students as research participants. But are college students truly representative of the general population? College students tend to be younger, more educated, more liberal, and less diverse than the general population. Although using students as test subjects is an accepted practice, relying on such a limited pool of research participants can be problematic because it's difficult to generalize findings to the larger population. Our hypothetical experiment involves children, and we must first generate a sample of child participants. Samples are used because populations are usually too large to reasonably involve every member in our particular experiment. If possible, we should use a random sample. There are other types of samples, but for the purposes of this chapter, we'll focus on random samples. A random sample is a subset of a larger population in which every member of the population has an equal chance of being selected. Random samples are preferred because if the sample is large enough, we can reasonably be sure that the participating individuals are representative of the larger population. This means that the percentages of characteristics in the sample, such as sex, ethnicity, socioeconomic level, and any other characteristics that might affect the results, are close to those percentages in the larger population. In our example, let's say we decide our population of interest is fourth graders. But all fourth graders is a very large population, so we need to be more specific. Instead, we might say our population of interest is all fourth graders in a particular city. We should include students from various income brackets, family situations, races, ethnicities, religions, and geographic areas of town. With this more manageable population, we can work with the local schools in selecting a random sample of about 200 fourth graders who we want to participate in our experiment. In summary, because we cannot test all the fourth graders in a city, we want to find a group of about 200 that reflects the composition of that city. With a representative group, we can generalize our findings to the larger population without fear of our sample being biased in some way. Now that we have a sample, the next step of the experimental process is to split the participants into experimental and control groups through random assignment. With random assignment, all participants have an equal chance of being assigned to either group. There's statistical software that will randomly assign each of the fourth graders in the sample to either the experimental or the control group. Random assignment is critical for sound experimental design. With sufficiently large samples, random assignment makes it unlikely that there are systematic differences between the groups. So, for instance, it would be very unlikely that we would get one group composed entirely of males, a given ethnic identity, or a given religious ideology. This is important because if the groups were systematically different before the experiment began, we wouldn't know the origin of any differences we find between the two groups. Were the differences pre-existing, or were they caused by the manipulation of the independent variable? Random assignment allows us to assume that any differences observed between experimental and control groups result from the manipulation of the independent variable. Issues to consider. While experiments allow scientists to make cause and effect claims, they're not without problems. True experiments require the experimenter to manipulate an independent variable, and that can complicate many questions that psychologists might want to address. For instance, imagine that you want to know what effects sex, the independent variable, has on spatial memory, the dependent variable. Although you can certainly look for differences between males and females on a task that taps into spatial memory, you cannot directly control a person's sex. We categorize this type of research approach as quasi-experimental and recognize that we cannot make cause and effect claims in these circumstances. Experimenters are also limited by ethical constraints. For instance, you would not be able to conduct an experiment designed to determine if experiencing abuse as a child leads to lower levels of self esteem among adults. To conduct such an experiment, you would need to randomly assign some experimental participants to a group that receives abuse, and that experiment would be unethical. Interpreting experimental findings. Once data is collected from both the experimental and the control groups, a statistical analysis is conducted to find out if there are meaningful differences between the two groups. A statistical analysis determines how likely any difference found is due to chance and thus not meaningful. In psychology, group differences are considered meaningful or significant if the odds that these differences occurred by chance alone are 5% or less. Stated another way, if we repeated this experiment 100 times, we would expect to find the same results at least 95 times out of 100. The greatest strength of experiments is the ability to assert that any significant differences in the findings are caused by the independent variable. This occurs because random selection, random assignment, and a design that limits the effects of both experimenter bias and participant expectancy should create groups that are similar in composition and treatment. Therefore, any difference between the groups is attributable to the independent variable, and now we can finally make a causal statement. If we find that watching a violent television program results in more violent behavior than watching a nonviolent program, we can safely say that watching violent television programs causes an increase in the display of violent behavior. Reporting research. When psychologists complete a research project, they generally want to share their findings with other scientists. The American Psychological Association, or APA, publishes a manual detailing how to write a paper for submission to scientific journals. Unlike an article that might be published in a magazine like Psychology Today, which targets a general audience with an interest in psychology, scientific journals generally publish peer-reviewed journal articles aimed at an audience of professionals and scholars who are actively involved in research themselves. A peer-reviewed journal article is read by several other scientists, generally anonymously, with expertise in the subject matter. These peer reviewers provide feedback to both the author and the journal editor regarding the quality of the draft. Peer reviewers look for a strong rationale for the research being described, a clear description of how the research was conducted, and evidence that the research was conducted in an ethical manner. They also look for flaws in the study's design, methods, and statistical analyses. They check that the conclusions drawn by the authors seem reasonable given the observations made during the research. Peer reviewers also comment on how valuable the research is in advancing the discipline's knowledge. This helps prevent unnecessary duplication of research findings in the scientific literature and, to some extent, ensures that each research article provides new information. Ultimately, the journal editor will compile all of the reviewer feedback and determine whether the article will be published in its current state, which is a rare occurrence, published with revisions, or not accepted for publication. Peer review provides some degree of quality control for psychological research. Poorly conceived or executed studies can be weeded out, and even well-designed research can be improved by the revision suggested. Peer review also ensures that the research is described clearly enough to allow other scientists to replicate it, meaning that they can repeat the experiment using different samples to determine reliability. Sometimes replications involve additional measures that expand on the original finding. In any case, each replication serves to provide more evidence to support the original research findings. Successful replications of published research make scientists more apt to adopt these findings, while repeated failures tend to cast doubt on the legitimacy of the original article and lead scientists to look elsewhere. For example, it would be a major advancement in the medical field if a published study indicated that taking a new drug helped individuals achieve a healthy weight without changing their diet. But if other scientists could not replicate the results, the original study's claims would be questioned. Dig deeper. The vaccine autism myth and retraction of published studies. Some scientists have claimed that routine childhood vaccines cause some children to develop autism, and, in fact, several peer-reviewed publications published research making these claims. Since the initial reports, large-scale epidemiological research has suggested that vaccinations are not responsible for causing autism and that it's much safer to have your child vaccinated than not. Furthermore, several of the original studies making this claim have since been retracted. A published piece of work can be rescinded when data is called into question because of falsification, fabrication, or serious research design problems. Once rescinded, the scientific community is informed that there are serious problems with the original publication. Retractions can be initiated by the researcher who led the study, by research collaborators, by the institution that employed the researcher, or by the editorial board of the journal in which the article was originally published. In the vaccine autism case, the retraction was made because of a significant conflict of interest in which the leading researcher had a financial interest in establishing a link between childhood vaccines and autism. Unfortunately, the initial studies received so much media attention that many parents around the world became hesitant to have their children vaccinated. For more information about how the vaccine autism story unfolded, as well as the repercussions of the story, take a look at Paul Offit's book, Autism's False Prophets: Bad Science, Risky Medicine, and the Search for a Cure. Reliability and validity. Reliability and validity are two important considerations that must be made with any type of data collection. Reliability refers to the ability to consistently produce a given result. In the context of psychological research, this would mean that any instruments or tools used to collect data do so in consistent, reproducible ways. Unfortunately, being consistent in measurement does not necessarily mean that you have measured something correctly. To illustrate this concept, consider a kitchen scale that would be used to measure the weight of cereal that you eat in the morning. If the scale is not properly calibrated, it may consistently under or overestimate the amount of cereal that's being measured. While the scale is highly reliable in producing consistent results, for example, the same amount of cereal poured onto the scale produces the same reading each time, those results are incorrect. This is where validity comes into play. Validity refers to the extent to which a given instrument or tool accurately measures what it's supposed to measure. While any valid measure is, by necessity, reliable, the reverse is not necessarily true. Researchers strive to use instruments that are both highly reliable and valid. Everyday connection. How valid is the SAT? Standardized tests like the SAT are supposed to measure an individual's aptitude for college education. But how reliable and valid are such tests? Research conducted by the College Board suggests that scores on the SAT have high predictive validity for first-year college students' GPAs. In this context, predictive validity refers to the test's ability to effectively predict the GPA of college freshmen. Given that many institutions of higher education require the SAT for admission, this high degree of predictive validity might be comforting. However, the emphasis placed on SAT scores in college admissions has generated some controversy on a number of fronts. For one, some researchers assert that the SAT is a biased test that places minority students at a disadvantage and unfairly reduces the likelihood of being admitted into a college. Additionally, some research has suggested that the predictive validity of the SAT is grossly exaggerated in how well it's able to predict the GPA of first-year college students. In fact, it's been suggested that the SAT's predictive validity may be overestimated by as much as 150%. Many institutions of higher education are beginning to consider de-emphasizing the significance of SAT scores in making admission decisions. In 2014, College Board President David Coleman expressed his awareness of these problems, recognizing that college success is more accurately predicted by high school grades than by SAT scores. To address these concerns, he has called for significant changes to the SAT exam.